All right, we are in chapter 5, and we're going to start paying attention to logarithms and exponential functions. So starting off with natural log of x and differentiation, or taking derivatives of natural log of x. Before we get into the calculus, we have to review pre-calc and math 3 or algebra 2, whatever year you're looking at this. First of all, we have to think, what does a logarithmic equation represent? A logarithm is an exponent. Meaning, if we want to evaluate the following logarithms, and we would do this without a calculator, the log base 3 of 31 is really asking you 3 to what power equals 81, right? So it's the same thing. So this logarithmic expression is an exponent. Okay, so our answer is 4. 2 to what power is 1/8? -3. If no base is showing, that's called a common logarithm, and it's base 10. 10 to what power is 100? 2. If we switch to natural log, remember natural log is the same as log base e. So the natural log base e of e to the 4th is just 4. You're saying, what is the exponent on the e to the 4th expression? Natural log of 1 over e, -1. Natural log of 1 or any log, any base of 1 is always 0, because in this case, e to the 0 equals 1. And an exponential expression with a logarithm of the same base in the exponent, so e to the natural log of 7, simplifies to just the result part, which is 7. 2 to the log base 2 of 7 would also equal 7. And then we also had these properties to expand and condense logarithms, and that helped us to solve equations and things. It's going to help us to take derivatives at times too. So if I have the natural log of x times y to the 4th, and it's understood even without parentheses that both of those values are inside of the logarithm, I can expand that out by saying that's the natural log of x plus, instead of the natural log of y to the 4th, remember we can move the 4 out in front. So plus 4 natural log of y. This one would be natural log of 3 plus natural log 1/2 natural log of x because of the square root there. And since we're dividing the product of 5 and y, it's minus natural log of 5, and it's also minus natural log of y. Otherwise, it would be minus the product, or the sum, of natural log of 5 and y, since you were multiplying those two, subtracting that whole thing, but I just distribute it right away. Be careful with subtraction or addition inside of a logarithm. So natural log of x squared minus 3 cannot be broken into two logarithms beyond that. So that doesn't simplify. You also can't pull the 2 out because that the 3 is not being squared as well. So natural log of x squared minus 3 minus natural log of x minus 2 natural log of y. Natural log of c plus, we have a square root here, so 1/2 natural log of c minus d. Now here, the entire result is being raised to the 5th power, so you can pull a 5 out here, and then you can expand this into natural log of x plus 1 minus natural log of y. Or you could just write 5 natural log of x plus 1 minus 5 natural log of y. So either way, those are equivalent because the exponent of 5 is applying to both of those. And then again, if we want to condense a sum and difference of logs into a single log, we're just using our rules in reverse. So it's a single natural log. Anything that's positive should be in the exponent. So x, 3 natural log of z would be times z to the 3rd. Anything that's negative goes in the denominator, so divided by y. This one is natural log of, so we've got a square root of t divided by a k squared, And since this is minus 1/3, it's going to be times a cube root in the denominator of t plus k. All right, and then still review from pre-calc, we want to, in Math 3, we want to solve these exponential and log equations. So if it's an exponential equation, you isolate the exponential piece, which it already is for 16. And then there are a couple of ways to think about this, but I always just say, well, the inverse of an exponential is a log. So I'm going to natural log both sides, because a natural log is kind of, you can just think of it as an operation. Natural log of e to the x is x, and my exact answer is natural log of 5. If I wanted to approximate, that would go into my calculator. If the e term, or whatever the base is not by itself, you need to first divide by 3 in this case, so isolate it first. And then we natural log both sides. Okay, so that gives us negative 2x equals natural log of 8/3. And now that can be expanded too. How much do we have to expand these? It does not, it does not matter. You just, if you're looking through a multiple choice answer, again, you would just have to pick out the correct answer. And then finally, x would be equal to either natural log of 8 minus natural log of 3 divided by negative 2, or more likely, if you divide by the negative or distribute the negative, you can flip this around. Natural log of 3 minus natural log of 8 divided by positive 2. So it could also be natural log of 8/3 divided by negative 2. So there are lots of ways your answer might show up. You just have to be able to manipulate and find it. All right, for my next one, if it's a logarithmic equation, you want to isolate the log, which it already is, and you need it to be a single log, which it already is. So then you write things in their exponential form. And again, you can either rewrite this in exponential form, thinking e to the 4th equals 2x minus 5, or you could think of it as base e both sides. E to the natural log of 2x minus 5 is 2x minus 5, and that would just equal e to the 4th. And then solving for x, I would add 5 divided by 2. So x equals e to the 4th plus 5, all divided by 2. That's my exact answer. For 19, there are 2 natural logarithms on the left. We need to condense that into a single natural log. And then you'd multiply x times x minus 2, so x squared minus 2x equals natural log of 15. Now, if you have natural logs on both sides, then you're using this one-to-one property that says if these two things are equal, then their results must be equal. So x squared minus 2x has to equal 15 for the natural log equation to be true. So that's just a quadratic to solve. And then we can factor. We have to be careful. I haven't mentioned this. For log equations, we have to make sure our answers are still in the domain. Remember, you cannot take the logarithm of 0 or any negative number. So I get 5 and negative 3. 5 would be okay to plug into natural log of x and natural log of x minus 2 because those remain positive. But negative 3 doesn't work. You can't take the natural log of negative 3 or the natural log of negative 5 as it would come out. So 5 is the only solution. And again, that's because thinking about this, e to what power is negative 3? You can't raise a positive number to an exponent and change its sign to negative. And then finally, the last type of equation we have is where we have to condense again. This one's log base 3. This would be division, so of x plus 2 over x, and it would just equal 2. Now, when you just have a logarithm on one side, you could base 3 both sides, if that makes sense to you, or you could also say 3 to the 2nd equals the result. So 9 equals x plus 2 over x. Multiply the x out. This is a rational equation, so multiply the x out of there. 9x equals x plus 2. 8x equals 2. So, sorry, I ran out of room. 8x equals 2. So 2 divided by 8 is 1/4. And 1/4 is okay to plug into x plus 2 and x because it remains positive. If this somehow was x minus 2, then 1/4 wouldn't work when I plugged it back in. And then finally, we do need to be able to picture these graphs. So in state, domain, and range. So the graph of e to the x, remember e is about 2.7 something, right? It's like 1/8 something. So it's just kind of good to know that. But when you're graphing it, e to the x, any exponential has a horizontal asymptote at y equals 0, has a y-intercept of 0, 1, and kind of increases like this. E to the negative x would be a y-axis reflection. So it still has the horizontal asymptote at 0, still has the point 0, 1. With that negative exponent, larger numbers you plug in, you're getting 1 over a huge number, so that's approaching 0. And as you plug in negative values, you're getting e to a positive exponent, which increases to the left. The natural log of x graph has a vertical asymptote. We're going to graph first, by the way. Go back and do domain and range. It has the point 1, 0. And remember, it kind of has this shape. The natural log of x minus 4, that's shifting to the right 4 units. So the vertical asymptote would get shifted to the right as well. And instead of having a point at 1, 0, I'd have one at 5, 0. And e to the x plus 4, so back to our e to the x graph, that got shifted up 4. So that would move the horizontal asymptote up 4 units. Instead of having a point at 0, 1, we'd be at 0, 5. Oh gosh. I'm not really allowing my e to the x graph to grow very quickly. There we go. That's better. All right, so what about domain and range? For exponential functions, the domain is all real numbers. You can put whatever you want in for x. So for all of these exponential functions, domain is all reals. The range differs depending on where the horizontal asymptote is. So the range for e to the x is 0 to infinity, not including 0. Same thing for e to the negative x. For e to the x plus 4, now we've got 4 to infinity because that's where the new horizontal asymptote is. And then for logarithmic functions, the range can be anything, all real numbers. The range is always all real numbers. The domain is based off of that vertical asymptote. So the domain for the natural log x graph is anything from 0 to infinity, not including 0. For natural log of x minus 4, now it's 4 to infinity, again, not including the 4. All right, so now a little bit of calculus. This is thinking about domain and range, right? What is the limit as x approaches infinity of e to the negative x? So as you're putting in infinity for e to the negative x, you're putting in, think of this as e to the negative infinity. Think of that as 1 over e to the infinity. 1 over something huge is 0. The limit as x approaches infinity of 4 over 1 plus e to the x. Again, think about direct substitution here. I know infinity is not a number we can really plug in, but it's okay to think of it like this. When I write infinity like this, I'm just thinking something huge. 4 over 1 plus e to the 1 millionth or whatever. You're getting 4 divided by a huge number, which is, again, practically 0. What if you plug in negative infinity? 4 over 1 plus e to the negative infinity is like 1 over e to the infinity. So really, it's like 4 over 1 plus 0, right? Because this term here is going to approach 0. So that limit is 4. What if I put infinity here into x squared plus 3 times e to the negative infinity? So anytime I see a negative exponent, first of all, I like to get rid of the negative exponent. So if I put in infinity, I get infinity squared plus 3 divided by e to the infinity. Now, both of these approach infinity, right? But I was taught to think of this as function races. We need to know that the x squared graph does not increase as rapidly as the e to the x graph, especially as you head out toward infinity. So I think of this as like little infinity divided by big infinity, which again is practically zero. Eventually, we will learn L'Hopital's rule to help us figure out more in a more systematic way that is zero. But even on the AP test, you can just think about it and write down the answer. It's not going to be a free response question. All right, what if we're putting a negative infinity? Well, negative infinity, even when you square it, think about the x cubed plus 3 graph. Even as you're going out to the left, the y values are approaching infinity, so that's still an infinity. And then when you plug negative infinity into a negative x, you're getting e to the positive infinity. So, well, no, yeah, we can think of it like that. So infinity times infinity is kind of, might be one of our indeterminate values. And again, we'll be able to show how this is true. But if you think of it, you've got a huge number times another huge number. This is going to come out to infinity. Remember, limits that are equal to infinity don't actually exist. We're just saying how they don't exist. All right, so a little bit more with the calculus, because I would consider limits to be calculus. So these are things that we need to memorize. I erased our trig derivatives off the wall, but we might put them back up and add some of these in too. So the derivative of the natural log of x is equal to 1 over x. And the derivative of the natural log of u, so something more than just x, like 2x or x squared or whatever, is equal to 1 over u, but then you have the chain rule, so times u prime, whatever that may be, whether that's 2 or 2x or whatever. And then the natural log of the absolute value of u would still be equal to 1 over u times the derivative of u. All right, so let's look at number 1. The natural log of x squared plus 1. U is x squared plus 1. du, well, I'm not going to write du because I don't have room there. Straight u prime is equal to 2x, right? So this is equal to 1 over x squared plus 1, 1 over u, times 2x, or just 2x over x squared plus 1. The derivative of x times natural log x. Product rule. It's been a while since we had to use all these little rules here. First times derivative of the second plus second times derivative of the first. X times 1 over x is 1 plus natural log x. All right, this is power rule to begin with, and then chain, of course. So 3 times natural log x squared. We don't really have like natural log squared x is not really an understood notation, so use parentheses in that case. If you don't use parentheses, then it looks like then it would mean that you're taking the natural log of x squared. Anyway, 3 times natural log of x squared, and then times the derivative of natural log x, which is 1 over x. And I could clean that up to 3 natural log x squared all over x, or 3 over x times natural log x squared, whatever. Next one is a chain rule. We have 1 over square root of x plus 1 times, what's the derivative of square root of x plus 1? That's 1/2 times x plus 1 to the negative 1/2. And technically there is a derivative of x plus 1, but that would just be 1. All right, so I have 1 over, now look at this, x plus 1 to the negative 1/2. is a square root of x plus 1, right? So in your denominator, you have x square root of x plus 1 times 2 times another square root of x plus 1. So that's actually just 2 times x plus 1. And actually, extra note about that, it should technically be 2 times absolute value of x plus 1, because the square root of x plus 1, the quantity squared, when you're taking the square root of a real number, you can't get a negative answer. So it would have to be whatever x plus 1 is. You'd have to force it to be positive. Or if you're not going to have that, really for all of these, I should probably be making little domain statements like, is there anything that could make this natural log not exist? In the x squared plus 1 case, no, because that's always positive, never 0. Here it should technically be like x needs to stay greater than 0. Same thing with this one. Same thing with this one. All right. All right, what about our next one? Natural log of, ooh, that fun thing. Okay, instead of saying, well, that's 1 over this times a really crazy like product rule within a chain rule within whatever, don't do all of that. Instead, expand this out first. Remember, it's usually easier to take derivatives of individual terms instead of like one big ugly thing. All right, so this is actually the natural log of x plus 2 natural log of x squared plus 3 minus 1/2 natural log of 2x cubed minus 1. Now I can take the derivative. Oh, you know what? I just realized what I've been doing. Sorry. At first we were okay. The derivative of this, the derivative of this. I really shouldn't be saying equals. I should be saying y prime equals f prime x equals. Sort of a bad example here. Okay, and then 5, this is still f of x, but now I'm going to write f prime of x equals 1 over x plus 2 over x squared plus 3 times the derivative of x squared plus 3, so don't forget your chain rule, so times 2x, minus 1/2 times 1 over 2x cubed minus 1 times chain rule derivative of 2x cubed is 6x squared. And then cleaning it up, I'm not going to do common denominators, but I am going to write that's the same as 1 over x plus 4x over x squared plus 3 minus 1/2 times 6 would be minus 3x squared over 2x cubed minus 1. So that's as far as I would take that. Same thing with number 6. You could do 1 over that square root and then do a pretty crazy and ugly chain and quotient, whatever rule. But even if you go through all of that and you do it successfully, this is probably going to be a multiple choice question, and you might not be able to get your answer converted to match whatever the choices are. So if you see something complicated inside of a logarithm and you could expand it, then you should. So this is 1/2 times the natural log of x minus 1 minus the natural log of x plus 1. You can have the 1/2 distributed through if you want. Y prime then will be equal to 1/2 the natural log of x minus 1 is 1 over x minus 1. Chain rule, derivative of x minus 1 is just 1. Minus 1 over x plus 1. And again, I'm just going to leave it like that. Of course, we could do common denominators and keep working on it if we needed to. The derivative of the natural log of the absolute value of cosine x. Why is that absolute value in there? So that we don't have to worry about domain restrictions and stuff, which we don't usually have to worry about, side note. Like, I should technically say what keeps this positive, but we're not going to get into all that right now. And again, in multiple choice AP problems, that's not going to matter. So this is going to equal It's not absolute value. Remember, it's not 1 over absolute value u. It's just 1 over u. So we're going to get 1 over cosine x, and then times the derivative of cosine x, which is negative sine x. That's negative tangent x. Let y equal natural log of x to the 3/2. Find the slope of the tangent line when x equals 1. So we need to find y prime and then evaluate it at 1. It's 1 over x to the 3/2 times the derivative of x to the 3/2 is 3/2 times x to the 1/2. And then that can be cleaned up, right? You've got 3, 1/2 minus 3 over 2 is negative 2 over 2. So you have a 2x down here, 3 over 2x. And then we're just evaluating y prime at 1. So that's 3 over 2. That's the slope of the tangent line. Find the relative extrema of natural log of x squared plus 2x plus 3. Relative extrema. So we need to know the critical numbers and then test signs on a number line. So let's find y prime. 1 over x squared plus 2x plus 3 multiplied by the derivative of that, 2x plus 2. And we're trying to do critical numbers, so let's factor what we can. Oh, I just realized x squared plus 2x plus 3 doesn't factor. Let's see, can it ever be negative? It has a vertex at, remember the negative b over 2a thing? Negative 2 over 2 times 1. Its vertex is at negative 1, and then when you plug negative 1 in, you get 1 minus 2 plus 3. So its vertex is at negative 1, 2, and then it opens up. So this denominator is always greater than 0. We're not going to get any critical numbers from the denominator. We can get a critical number from setting the numerator equal to 0. And so when we test on a number line for y prime and what's happening with y, if I put in something like negative 2, remember the denominator is always positive, so 2 times negative 1 divided by a positive is negative. And if you put in something greater than negative 1 like 0, you're going to get 2 times a positive 1 divided by a positive. Find the relative extrema. So now I should figure out what is y of negative 1. It's the natural log of 1. Oh, I already found that. Natural log of 2. So there's a relative minimum at negative 1 natural log of 2 because y prime changes from negative to positive at x equals negative 1. Find dy dx where natural log of xy plus 2x equals y. So find dy dx. How do we do this? This is one of those differential equations, right? Remember, we want to say, well, let's differentiate with respect to x on both sides of the equation. So this y becomes dy dx. And over here, we take derivatives. We have 1 over xy times, what's the derivative of x times y? It's the first function x times the derivative of the second, dy dx, plus the second times derivative of the first. And then derivative of 2x is plus 2. So we have dy dx is in 2 places in this equation. We need to work on that a bit. So let's see. There are a few things I could do. I'm going to clean up this mess right here first. So we have dy dx divided by, these x's cancel, but divided by y, plus y divided by xy would be 1 over x. okay, plus 2 equals dy dx. Let's subtract this dy dx over. 1 over x plus 2 equals dy dx minus dy dx over y. And then we want to factor out a dy dx. That would leave me with 1 minus, if you factor that out, you get 1 over y. So the complex solution is 1 over x plus 2 divided by 1 over, divided by 1 minus 1 over y. It's very likely that they will say, multiply this by xy, so that we don't have all this complex fraction stuff. So you need to be able to pick that answer out too. That would be y plus 2xy divided by xy minus x. All right, either thing, either way. Or you can multiply by negative xy over negative xy, whatever. It doesn't matter. Okay, that's it for today's notes. We have homework, I think, number 27 tonight.